Hi guys, welcome to your 10-2 notes on simplifying radicals. By the end of the day, you will be able to simplify radicals involving products and quotients. Now I talk about radicals. Let's show you what the parts of a radical expression are. A radical expression is an expression involving a radical symbol. This guy right here, we call him the radical. And what a radical does is it will undo a square. For example, if I have some number like m squared, I take the radical of that, those will cancel out, and that gives me just m. So in a radical, you can have an index right here. N is called our index. You'll notice on my expression over here, there is no index. If there's not an index right here, it's implied that the index is 2. So that 2 will undo the 2 on my square. Yep. Okay. So we've got an index, usually 2. It can be 3, and that's called a cube root. And then what's underneath your radical symbol, whatever this number is, we call that our radicand. Radicand. And that's going to be our big focus of the day today. We'll look at what is underneath our radical symbol. We'll look at our radicand. So, our key idea of the day is to be able to simplify a radical expression. Now, a radical expression is in simplest form when 3 conditions are met, when 3 things happen. First, the radical, or rather, the radicand, what is under your radical symbol, cannot have any perfect square factors. We don't want it to have any perfect squares underneath our radical. So to get rid of those, to determine if we have them, we factor the radicand. We figure out if there are any squares in here. Secondly, once there are no perfect square factors, we need to check that the radicand doesn't have any fractions inside of it. And then finally, we don't want any radicals to be in the denominator of a fraction. If that is true, we're going to do a process called rationalizing the denominator. Now you remember that the denominator of a fraction is the bottom part. That's what's on the bottom. So let's look at some examples and show why they are radicals. Rather, let's look at some radical expressions and show why they're simplified. So here, 3 times the square root of 5 is a radical expression, and it is simplified because 5 doesn't have any perfect square factors. There are no fractions here, and because there's no fractions, there's no radicals in the denominator. 9 times the square root of x is also simplified because x doesn't have any perfect square factors. You can't factor a variable, it's just x. There's no fractions, and because there's no fractions, the denominator doesn't have any fractions in it. Or rather, the denominator doesn't have any radicals in it. And then finally, the square root of 2. Well, what's underneath our radical symbol? Our radicand is just 2. Here, I'll highlight the radicands to make this easier. So here our radicand is 2. That doesn't have any perfect square factors. The radicand doesn't have a fraction in it. It's okay that there is a fraction, but there's not a fraction underneath our radical symbol. And then finally, there are no radicals in our denominator here. It's just a plain 4. Now, let's look at 3 times the square root of 12. That is not simplified because 12 can be factored into 3 times 4, and 4 is a perfect square. So that's not simplified. Next, we have the square root of x over 2. Well, that's a fraction, and because we have a fraction in our radical symbol, that is not simplified. And then finally, we have 5 divided by the square root of 7. Well, here in our denominator has a radical in it. So that is not simplified. Now our goal today is to get all of our radical expressions simplified. They all fit these descriptions. So what we're going to do is we are going to look at 3 ideas that will help us simplify. Basically, we're going to look at the perfect squares and how to find them and get them out from under our radicals. And then we'll look at when we have fractions and how we can get radicands out of a fraction. And then finally, we'll look at when we have a radical in a denominator of a fraction, and we will rationalize that denominator. So let's start out with finding our perfect square factors. We're going to use the multiplication property of square roots. The multiplication property of square roots says that if you have 2 numbers greater than 0, that is if a is greater than 0 and b is greater than or equal to 0, then I'll make it yellow. So if you have the square root of a times b, then you can break that up into the square root of a times the square root of b. Now, why does this work? Well, let's look at an example. The square root of 36, I can break that up into the square root of 4 times 9. The square root of 4 times 9, because 36 is equal to 4 times 9. And I can break that up even more. That's the square root of 4 times the square root of 9. Now the square root of 4 is 2, and the square root of 9 is 3. And 2 times 3 is 6. So there you have it. There's proof that the square root of 36 is 6. Now we're going to use this rule to simplify 2 radical expressions. Let's look first at the square root of 72. Now that's not simplified because 72 can be broken up into factors. When I look at 72, my first thought is to split it up into 9 times 8. So let's do that. The square root of 72 is equal to the square root of 9 times 8. Then we can split the radical into 2 radical expressions. So this is the square root of 9 times the square root of 8. Now the square root of 9, that's 3. You know what? I think I'm going to write this vertically. I think that will help a lot. Okay. There you go. So the square root of 9 is 3. But 8 can still be broken up into squares because 8 is equal to 4 times 2. And 4 is a perfect square. So just like up here, when we split up the square root of 9 as 3, we can split up the square root of 4 is equal to 2. So that's equal to 3 times 2 times the square root of 2, which is 6 times the square root of 2. And that is the square root of 72 in its simple form. Now that did take kind of a lot of steps. So if you want to split it up a different way, you can do that and it would take less time. So let's say we want to do this problem again. We start out with the square root of 72, but this time instead of splitting up the square root of 72 as 8 and 9, we can split it up as 36 times 2. Now I did that because 36 is a perfect square. So if we split this guy up again, that's equal to the square root of 36 times 2, which is the square root of 36 times the square root of 2, which is 6 times the square root of 2, because the square root of 36 is 6. And there you have it. That is still our same correct answer in half the time. So no matter what you do, it doesn't matter how you split it, as long as you keep going until it is most simplified. Let's do another example. So here in B, we have negative m times the square root of 80m to the 9th power. So we're going to split this guy up. First, again, the reason we can split it up is because we're using the multiplication property of square roots. So I'm going to split up the radical, which is this part right here. I'm going to split him up to 80 and m to the 9th power. So we keep our negative m out in front the same. Now we have the square root of 80 times the square root of m to the 9th power. Now we want to split up each of our radical symbols into square roots. So we keep negative m the same, and 80 is equal to 16 times 5. You could also do 8 times 10, but that will take you a couple extra steps. So 80 is equal to 16 times 5, and the square root of m to the 9th, that's equal to m to the 8th power times m. So here we have negative m times the square root of 16 times the square root of 5 times the square root of m to the 8th times the square root of m. Now we can simplify all of the square roots that have squares. So the square root of 16 is going to be 4. The square root of m to the 8th is m to the 4th power. So we have negative m times 4 times the square root of 5 times m to the 4th power times the square root of m. Let's hit pause 1 second. Where did this come from? How did I know that? Let's go ahead and review our powers of exponents, or our powers rules. So if you have m to the 8th power, I know I can split that up by writing, well, 8 is 4 times 2. According to our powers rules, that's the same thing as m to the 4th power raised to the 2nd power. Because again, if you have exponents that are multiplied by each other, that's like raising those exponents to another power. So m to the 8th is the same thing as m to the 4th squared. So m to the 8th is a perfect square. Now we're almost there. I'm going to combine all of my radicals together by undoing our rule. And undoing my multiplication property of square roots, I can take two separate radicals and I can put them under the same radical. So I'm going to do that real quick by combining them as the square root of 5 times m. And that leaves me with negative 4m times m to the 4th power. Now I'm almost done, except now I can combine m times n to the 4th power. That's equal to negative 4m to the 5th power times the square root of 5m. And that's it. That's our solution. Now for some people, you might argue, hey, that doesn't look any more simple than our original problem. But let's check our three conditions and see if they're met. Do we have any perfect square factors under our radical? Whoops, we don't. Do we have any fractions? No, and therefore our denominator is rationalized. Okay, now that's the first step. That's our first condition met. Now let's see what happens when we have fractions. When we have fractions, we're going to call on not only the multiplication property of square roots, but also the division property of square roots. And the division property of square roots says that if you have two positive numbers, a and b, then the square root of a over b is equal to the square root of a all over the square root of b. Let's explore this with some real numbers. For example, if we have the square root of 100 over 25, we can split that up into the square root of 100 over the square root of 25. The square root of 100 is 10. The square root of 25 is 5. 10 divided by 5 is 2. Done. Or you could check this out from the beginning and you could say, wait, the square root of 100 divided by 25, well, 100 divided by 25 is 4. So that's the square root of 4, and the square root of 4 is 2. So it works. Okay. So we're going to use that same knowledge to simplify each of these two expressions. So let's go ahead and break this up to two radicals. That's the same thing as the square root of 144 divided by the square root of 9. Now the square root of 144 is 12, the square root of 9 is 3. 12 divided by 3 is 4. So the square root of 144 divided by 9 is 4. Sweet. You also could have done this by knowing that 144 divided by 9 is 16. So the square root of 144 divided by 9 is the square root of 16, which is 4. There you go. But sometimes you can't always get there that fast. So let's use all of our knowledge on example 2b. So again, we're going to split this guy into two radicals. We have the square root of 8x squared all over the square root of 25. Starting with our numerator, with what is on top, we can split that into two radicals. So we have the square root of 8 times the square root of x squared all over the square root of 25, that's 5. Sweet. Then we can break up the square root of 8 by saying, well, that's the square root of 4 times 2. And the square root of x squared, well, that's just x. And then over 5 stays the same. Keeping on going, we can split up the square root of 4 times 2 as the square root of 4 times the square root of 2. Then we have our x all over 5. The square root of 4 is 2, so that gives us 2 times the square root of 2 times x all over 5. You could leave it like that, but for some people it's super confusing and they think that the x is underneath the square root, but it's not. So I like to rewrite it as 2x times the square root of 2 all over 5. And I expect that you write them as well. So if you have anything times the square root, please put that out in front of it like we do right here. So that's what happens when you have a fraction. So those are our first two conditions met. We got all of our perfect squares out of the radicand. There's no fractions involved. Now what happens, or rather, there's no fractions underneath our radical, but what happens when you have a radical in your denominator? How do you get rid of that? We're going to do a process called rationalizing the denominator. Now when you have a radicand, that's again what is under your square root, like this, in a denominator, remember your denominator is the bottom part of your fraction, you're going to remove the radical by multiplying both the numerator and the denominator by the same radical expression. This process is called rationalizing the denominator. You're going to make it a rational number. So let's do that. We're going to start out by multiplying by our denominator. So we multiply by the square root of 3, and we multiply by the square root of 3. We're multiplying both top and bottom by the square root of 3 because the square root of 3 divided by the square root of 3, that's equal to 1. This does not change the expression at all. So we take this guy, we multiply him by original expression, and there is no change. That's a super important idea. Go ahead and leave that for yourself. Say, hey, this equals 1. So when we multiply by this, it doesn't change our original expression. So we can multiply by 1 with no consequence. And that gives us the square root of 2 times the square root of 3 all over the square root of 3 times the square root of 3. Sweet. Now the square root of 2 times the square root of 3 is the square root of 2 times 3. It gives us the square root of 3 times 3. So we have the square root of 6 all over the square root of 9. The square root of 9 is 3, So it goes the square root of 6 all over 3. Now, you may be noticing, hey, we've got a fraction, and we've got a 6, and we've got a 3 here. So those should reduce, right? Wrong. These guys do not reduce. Why? Because it's got that square root on top, the square root right here, that doesn't mean this is 6. This means this is the square root of 6. And that cannot reduce. Because it's under a radical, this 6 will not reduce. So that's it. That's as simple as it gets. The square root of 6 over 3. By the way, did you guys notice how we multiplied square root of 3 times the square root of 3, and that left us with 3? That will always be the case. So if you have the square root of 3, or if you have the square root of something times itself, you just get what's in your radicand. It's always 3. Not always 3. It's always what's underneath your radical. Okay, so here's a little shortcut for you. If you have the square root of x times the square root of x, that will always be x. Always. Let's do our last one. And let's also remember that the square root of x times the square root of x is x. Why? Well, that's because the square root of x times the square root of x, we can combine those, giving us the square root of x times x, which is the square root of x squared. Square root of x squared is x. So there you go. Okay, so we look at this guy and we say, oh, yikes. We've got a square root in our denominator. That's not okay. We need to multiply top and bottom by our denominator, by our square root. So on top, we are given 5 times the square root of 8. We can do our shortcut down here. Square root of 8 times square root of 8 is just 8. Nice. And we're almost there. Except this guy right here, the square root of 8, that's not simplified. Didn't we just simplify that? Where did we go? Oh yeah, up here. We found that the square root of 8 is equal to 2 times the square root of 2. Because we broke up the square root of 8 into the square root of 4 times 2. So the square root of 8 is 2 rad 2. So let's simplify that guy real quick. So we can rewrite that as 5 times 2 times the square root of 2 all over 8. And we're almost done. You see this 2 and this 8 right here? We can reduce that. So let's reduce a 2 out of there. Cross out 2, give it a 1. Cross out an 8, gives us a 4. So our fraction reduces to 5 times the square root of 2 all over 4. And we're all set. So it's okay that we have a fraction. We don't have a radical in our denominator, so we are all set. So again, as you are simplifying your radical expressions, make sure that each of these are set. You don't want any perfect square factors underneath your radical. You don't want a fraction underneath your radical. And if you have a fraction, you don't want a radical in the denominator. So make sure you rationalize the denominator like we just did. I hope you have a fantastic time on your homework.